Okay, so in this video I'm going to prove Cauchy-Goursat's theorem for polynomials. So Cauchy-Goursat's theorem says if we have a function defined on a simply connected domain and we have some simply closed contour in that domain, so let's see be a simply closed contour. So this just means that we have this curve, and for example this wouldn't be a simply closed contour, so this would be not an example of one. The reason is because there's like a point where it overlaps with itself, and so a curve like this would not be simple. So an example would be something like this. This would be a simply closed contour. So we have a simply closed contour, and Cauchy-Goursat's theorem says that the integral of a function, a complex function, over this contour is 0. So this is the complex plane. So we have the imaginary axis and the real axis. And we're going to just prove this for polynomials. The full theorem, the way it's usually proved requires some tricky business. But if we just prove it for polynomials, we can use something called Green's theorem from vector calculus to make our lives easier. We don't have to do anything fiddly. Here's what we're going to do. Let P be a polynomial. So the theorem says that we just need to define that P just has to be defined on a simply connected domain. But because it's a polynomial, we can define it on the whole of the complex numbers anyway, so we don't really have to worry too much about the domain having to be simply connected or anything. So we just want to prove that the contour integral of this polynomial, this complex polynomial, over this simply closed contour is 0. The first step would be that we can actually write z as x plus iy, and dz as dx plus I dy. So we can do something like this. Okay, but the thing we're doing is we're making new functions, x and y, which are really functions of z, right? So we really haven't done anything. We're writing the same thing again, but where x is just the real part of z and y is just the imaginary part of z. So we're just doing an extra step, right? We can now separate this out into its real and complex parts. Because it's a polynomial, the real and complex parts will just be polynomials in x and y. So we can write it as some contour integral c over u, which is going to be the everything in the polynomial that's real, and then we have a part that's imaginary. I think we should have a just quick example of what this looks like. So just an example. So suppose a polynomial is p of z equals z squared, right? What would u and v look like? Well, then we have that p of x plus iy would be x plus iy squared, which is x squared minus y squared, which would be the u. So we have this. Then we have this cross term, which is plus I times 2xy, and which would be v. So let's carry on. And you can see these are polynomials in x and y. It means like if you just suppose one of these was a constant, then it just becomes an ordinary polynomial. So so either x or y is constant, then it becomes an ordinary polynomial. Okay, let's get back to this. Okay, right, so what we want to do now is we want to expand it out, because we want to use Green's theorem on this. Okay, why are we allowed to use Green's theorem in this case? Because we can't use it in general. We can't use it if p was not a polynomial, it was just some random function. We can use it because the partial derivatives are continuous. The partial derivatives of p with respect to x and y are continuous. Okay, so in particular u and v, the partial derivatives are continuous. Why are they continuous? Well, the partial derivatives, like we said before, when we're taking partial derivatives, we assume that the thing we're not taking the derivative of, the variable or variables that we're not taking the derivative of, are constant. So we can just pretend it's a polynomial. And when we take a derivative of a polynomial, the result will be another polynomial, and that will be continuous, right? And we also have to check that's continuous in all the variables, but that actually, it turns out that it is true, that it is, in fact, that multivariable polynomials are continuous. So we have that, so we can use Green's theorem. So we have, to use Green's theorem, we just want to get it into the right format of Green's theorem. For that, we need to expand this out. So let's put the x terms here. So v plus I, e plus iv dx, and then plus u plus iv dy. So really, and oh wait, don't forget there's an I here as well. So now we want to use Green's theorem. So this next step is Green's theorem. So Green's theorem says that this is equal to. So right now we're looking at this simply connected curve here, and now we instead of integrating over the curve, we're going to integrate over this area, which we're going to call D. Right, and this is going to be double integral over D. And now we're going to take we're going to take the partial derivative of this part with respect to y. So u plus iv y. Subtract the partial derivative of this part with respect to x. U plus iv x I. So let's actually group the terms that are real and imaginary together, and if we do that we get the double integral. So we get a partial of u y, and then we have this, in this case we have an I times I, which is minus 1, then there's minus here, so it's plus vx. Then we have a, so let's do plus, put the I at the front, iv y, and then we have an I u, which is a negative partial with respect to x, so negative u x is an integral over an area, so dA. Now we want to recall the Cauchy-Riemann equations. What do the Cauchy-Riemann equations say? It says that the partial derivative, since p is an analytic function, these u and v's, they satisfy the Cauchy-Riemann equations, where u partial with respect to x of u is partial with respect to y of v, and partial of u with respect to y is negative the partial of v with respect to x. Okay, you might be able to see that over here, look, if we plug in minus vx into this part here, then this entire part cancels and gives us 0. Same thing over here, if we plug in ux equals vy, then this part also becomes 0. So we're integrating 0 over this region D, and so we're integrating 0 dA, which gives us 0. And so we have that our integral is 0, and this gives us Cauchy-Goursat's theorem in the special case where f is a polynomial. So thanks for watching. See you next one.